Okay, so I make it 2 o'clock. So welcome everyone to the Applied and Computational Maths seminar. Today we've got Matthias Rauter, as you can see here from the University of Oslo's days. He's going to talk about his work, but since then he's also been working for the Austrian government doing contracting in terms of flood modeling and hazard mitigation. But then before that, when I met Matthias, he was at the University of Innsbruck working in the engineering department. So, he's had a wide spectrum of experiences, engineering, mathematics, geosciences, and now he's going to go back to Oslo for a software developing role. So, man of many talents. And today he's going to talk to us a lot about the kind of crux of all of these different skills, and that's multi-phase modeling of landslide generated tsunamis. So over to you, Matthias.
Yes, thank you very much, and thanks for the invitation. And you put it down in a very nice way. I never thought about it that way, but this work is actually a lot of different things coming together, from programming to engineering to geosciences. At the same time, it's very applied here in a circle of mathematicians. I hope I can fit in, let's say it like that. And yes, this is basically my thesis that I wrote at the University of Oslo between 2018 and 2021. And we tried to simulate landslide tsunamis with the Navier-Stokes equations. And as an introduction, I quickly want to explain a little bit the problem that we are trying to solve. And this example here is an incident that happened very closely to where I grew up. I'm actually Italian, and this incident happened in northern Italy in the 60s. And what you can see here is the Bajant Dam, an aerial photography on the left side, and a cut through the dam and the mountain on the right side. And when the dam was built in the beginning of the 1960s, and then the water level increased. And this led to water mitigating into this lower porous layer of soil here on the mountain flank. And this intrusion of water increased the pore pressure in this area. So basically the whole mountain slope was lifted up and the grains were losing contact with each other, and the whole mountain collapsed, fell into the artificial lake, and generated a wave that overtopped the dam and destroyed the village of Longarone that was located just below the dam. And here on the left side, you see again an aerial photography of the situation that we still have right now. So the lake is completely filled up with soil and rock material. And we wanted to simulate this, and it's quite a difficult problem that involves a lot of different things. So the concept we had was that we want to include only the really, really important effects and first order processes. And we started with thinking about what do we actually have to account for. And first of all, we have multiple phases. We have, of course, the water phase that represents the wave and the tsunami and everything. We also have the air phase, which is kind of a passive phase where nothing else is involved. And then we have, of course, the rock material. And the rock material it's quite a difficult material to describe. It's plastic, it's frictional, it can be like a liquid, it can be like a solid. So we need some really good constitutive models for that. And then, as I told you, the pore pressure was increasing and destabilizing the whole flank. So that's also very important. And whenever you have pore pressure, you have pore fluid flow. And that, of course, involves permeability and all of these things. Last but not least, we have very complex surface waves. So we don't have shallow waves, which basically means we cannot use simplified depth averaged models. We have to solve the complete three-dimensional problem. And therefore, we have to rely on the Navier-Stokes equations. And we wanted to bring all of this together into one model that can kind of solve this whole process from the initialization of the slide to the runout, to the generation of the tsunami and the inundation of the tsunami elsewhere. And how we built this up was basically we started with the waves. We started with the wave because here are only fluids involved, and the ordinary Navier-Stokes equations are already quite good for this part of the problem. Then we added a complex constitutive model for the soil material, and in a third step, we added pore pressure and permeability effects to this model. And in a fourth and last step, we put all of these things together so we can simulate the whole process chain, and then we simulated a whole three-dimensional problem with it. Yeah, and this content is basically also the 4 papers that I wrote for my thesis. So yeah, let's start with the first part, basically looking at the Navier-Stokes equations and how we can use it to simulate impulse waves. And here you see them. They are quite famous set of equations. This is one of the many forms that the Navier-Stokes equations can have. And these are basically 2 equations. One is derived from the conservation of mass, and the second equation is derived from the conservation of momentum. And in the incompressible Navier-Stokes equations, the mass conservation equation falls apart, and all that remains is this constraint on the velocity u. And then what's left is the momentum conservation equation, and here you have a lot of terms. So first off, the acceleration of the inertia force, then you have convection of material and convection of momentum. You have gravity that can accelerate things. You have the gradient of the pressure that pushes things in one direction or the other. And of course, you have the shear stress, which is kind of the internal forces in a fluid or the frictional forces in a fluid. And how I like to think about this set of equations is that this constraint on the velocity determines the pressure P at all times. So I don't have to think about this constraint nor the pressure. I just know my pressure at all times because of this constraint, and I can then use the second equation as an evolution equation for the velocity u. And this is also the way that these equations are usually solved in commercial products, in commercial software. A little bit tricky is this shear stress term. And the shear stress term, as I said before, it represents the internal forces in a liquid. And we assume in a first step that the shear stresses are proportional to the shear rate, which is basically the symmetric part of the gradient of the velocity. And this is a measurement for the deformation in a fluid and thus proportional to the shear stress. And this brings you already very far for simple fluids. And this model then has 2 parameters, the fluid viscosity eta, which determines how big the internal forces are, and the density basically determining the weight and the inertia of the fluid. And we can use this already to do a lot of things. A problem with waves is that you have always more fluids involved. You have, of course, the air involved, and you have the water involved, the water that is creating the wave. And in that case, you have, of course, not constant viscosities and constant densities anymore in your simulation domain. So you have a high density here where the water is, and you have a low density here where the air is. And a very simple and elegant solution to solve that problem is to introduce these markers. I call them alpha here. And these markers that basically move with the liquid, so we can define this very simple evolution equation is just a convection equation for these markers. And therefore we know at all times where our heavy water is. and where the light air is. And we can then calculate an effective density and an effective viscosity by using these water markers that are either 1 or 0. And that's basically all that we need to simulate some waves. So let's do it. And of course, we don't have yet granular material, but there is a set of experiments from a Canadian group that ran tank experiments, and they used pure water for the slide. So that means I don't have to implement these complex material models to test the capabilities of my model to simulate waves. And here you see the setup. They basically had here the starting mass for the slide, and down here a very long water tank where the wave could build up and propagate. And here you see the respective simulation with the Navier-Stokes equations. Everywhere where there is color, there is my heavy fluid, there is my water, and the color marks the velocity. And as soon as I start the simulation, you see the slide is accelerating. It's getting very thin, so it's quite a challenge to resolve the flow fields in this area of the slide. But we worked it out, and you can see here the slide hitting the water. A quite big wave is building up and is then traveling from left to right along the tank. Here it's inundating on the opposite shore, and then it's getting reflected. And in the experiment, they were measuring the water level elevation with a set of wave gauges that was distributed along the tank. And we can, of course, do the same in the simulation and then compare the measurements. And they fit quite well here at the beginning. They are a little bit worse here after 6 meters. The reason for that is that the wave was breaking sooner in the experiment than in the simulation. But at the next wave gauge, the wave in the simulation is also breaking, and they fit together nicely again. And overall, you have quite a nice fit considering the complexity of the problem involved. And we use this as a kind of to get the first idea how good the Navier-Stokes equations can simulate the waves. And we were actually quite surprised by how good this was. And the error was always below 25%. And this is actually quite something an engineer can work with. So we were quite happy, and we continued with this approach. Of course, now we needed some plasticity models in our model in the Navier-Stokes equations in order to simulate our landslides. And how to do this, to show how to do this, I want to come back to the momentum conservation equation of the Navier-Stokes equations. And and as I mentioned before, all of these terms are basically determined. So the acceleration and inertia, the convection and the gravity, they are as they are. And the pressure is fully determined by the constraint on the velocity. So everything where we can play around with is this last term here, the shear stress term. So I took this one here out again, and you see in the shear stress term, here I write the deviatoric for the shear stress, all you have in there is the viscosity. So if we want to change how a material behaves, we have to change the expression for the viscosity. And we already saw the simplest case where the viscosity is basically constant. And that means that the shear stress and the shear rate are always proportional to one another. And then we speak of a Newtonian fluid. Of course, soil and sand and rock is not behaving in such a way. We also have internal shear stresses when the material is standing still. It's basically stable. So we have a constant shear stress in the material. But of course, we are mathematicians, or you are mathematicians, and we can just define a viscosity that after multiplication with the shear rate gives us this constant shear stress. And basically that's what I did here. This is already quite good, and a lot of people use this model to simulate slides. It's not yet good enough. We actually need to implement a frictional material. And in that case, the shear stress is proportional to the pressure. So you know it when you pull something heavy, the heavier the object is, the higher the friction is on the ground. And we can easily implement this by defining a viscosity that is proportional to the pressure and a constant mu. And this mu, this is exactly the friction coefficient, the coefficient between pressure and shear stress. And in the simplest case, this is something like a Colombian or more Colombian friction. And we can use this to now run our first granular flow simulations. And here we chose the simplest experiments that contain the whole chain from slight release to flow to deposition. And these are basically granular collapse experiments. So you see a column of granular material here, and we have a door here, and we open the door, the material will slide out and come eventually to a rest. And this is now the simulation with the Navier-Stokes equations of exactly this experiment. The color here now marks the pressure, and the arrows mark the velocity of the slide. And you see where there is high pressure in this red zone, we have a very high viscosity, and the material cannot flow apart. But here in this triangle where the pressure is low, the viscosity is low, and the material can start to flow. So the material starts to accelerate here, it runs out, and after a while we reach a stable slope inclination, and the dashed line here is the final slope of the experiment, and it fits fairly well. Of course, we miss here a little bit of material, and the reason for that is that the granular material is dilating while it's flowing. And this is, of course, not included in an incompressible model, so we miss this volume in our final pile shape. But overall, again, quite a good fit with the experiment and good enough for practical application. So that brings us to the next part, and that is pore fluid effects. And I told you before that in the case of Vaillant, the pore fluid was reducing the stability of the slope and actually leading to the slope. So this is really important to include, because every slide that generates a tsunami will always be involved with water in some way. So you always have pore fluid effects, and it's really, really important to include them. And why is this so important? Well, I told you before that the constraint on the velocity determines the pressure at all times. So we know the pressure at all times, but not all pressure is equal. And you see it here. So you can have an effective pressure that's represented here by these red arrows, and the effective pressure represents the forces between the grains. And you can also have pressure in the pore fluid that's here represented with the blue arrows, and that's pressure in the pore fluid. And why is it important to distinguish between effective pressure and pore pressure? The reason is that only effective pressure, only pressure between grains leads to friction. So only the effective pressure leads to stability. The pore pressure, on the other hand, leads to a bad stability. So you can have the situation here where most of the pressure is held by the grains, and that will give you a very high shear strength, a very high shear stress in the material. But you can also have the situation down here where most of your pressure is in the pore fluid, and then you will have a very bad shear strength and thus a very bad stability. And of course, a slide will behave very differently, and it will reach very different velocities depending on the situation we are in. And so we need to really distinguish between these two kinds of pressure. Thankfully, there is a very simple theory in soil mechanics that allows us to distinguish between those two. And that is called the critical state theory. And in its absolutely simplest form, you have three states. You have a very loose packing of grains where you have no contact between grains, and therefore you have no effective pressure. If you then pack your grains a little bit closer, you will get a few contact points between grains. You will then start to develop some effective pressure, and at some point your pressure will go to infinity because you start to pack your grains very closely and you start to reach the point of the densest possible packing. We can, of course, then again, as good mathematicians that we are, just define a line that kind of runs through the states in one manner or another, such that nature is approximated as good as possible. And I just used this very simple line here as a first approximation with some further refinements along the way. But basically it says you have here a point where your pressure starts, and you have here a point where your pressure peaks to infinity. This, of course, now gives us a different problem, and that is that we need to know the packing density of our grains, of our soil material. And for that, we need to track the phases. So we first, of course, need to define them in a very nice way. And we define them, the phase fractions, as the volume occupied by grains over the total volume. And of course, I can do the same thing with my liquid phase to track my liquid phase. And then I can define a Navier-Stokes equation just for that particular phase. And I can do this by basically pre-multiplying the Navier-Stokes equations with my phase fraction, phi g. And again, the terms are the absolute standard terms of the Navier-Stokes equations. I have again my inertia, I have compaction, I have the shear stress that we know from before, how to control it. Here we split now the pressure, Here we split the pressure into effective pressure and pore pressure. As we saw, it is required. We have again gravity as before. And this term here, this one is new. I will speak about it very shortly. Of course, we can and have to do the same thing for the pore liquid. So in order to describe the pore liquid, the equations are exactly the same. The only difference is that the effective pressure is not acting on the pore liquid. The effective pressure is only acting on the grains. And again, back here, we have this new term. So what is this new term? Well, by pulling apart our system, by pulling apart our simulation domain in two parts, in a part occupied by the grains and in a part occupied by the liquid, we created a new boundary. And of course, we have forces acting on this boundary. And of course, we have to include this in our model. So the force that is acting on one phase is acting the exact opposite way on the other phase. And this is included here by the same term and opposite signs. And of course, if you want to speak about a physical explanation or a physical representation of this term, then this would be the drag term of the grains that move in liquid. And that's again basically everything that we need to run some simulation. Of course, we need to close the system. We need again the nonlinear viscosity for the grains that we introduced before. We need this simple equation for the particle pressure as a function of the packing density. And we need a very simple equation for the drag between the grains and the liquid. Here I used the absolute simplest equation that I could find. It turned out to be good enough for a lot of things. As I mentioned before, I started with very simple equations, but I used some refinements along the way, and I just wrote them here as an additional contribution to the pressure as a function of the shear rate and the backing density. And the same here with the viscosity, the grain viscosity. The friction coefficient mu is usually modeled as a function of the shear rate and the backing density of the grains. And with this now we can run simulations as before, but this time we can also run simulations where the pore pressure had a noticeable effect on the outcome. And Rondon et al. Conducted such experiments in 2011, and they used a very high viscosity fluid in order to increase pore pressure effects. And they used very small glass beads, because again, in order to include to maximize these effects of the pore pressure. And they ran two initial states of these experiments. They ran a dense experiment and a loose experiment. And here you see first the simulation with the dense experiment. And what you can see here is the pressure on the left side, the pore pressure, and on the right side, the effective pressure. And in the dense case, you see that all the pressure is in the effective pressure, all the pressure is between the grains. And the pressure in the liquid is actually very low. The pressure in the liquid is lower inside the slide than it is outside the slide. So the slide will actually pull water in and thus reduce its backing density. And that you can see here. And basically by pulling water in, the backing density is lowered, the effective pressure is lowered in this triangle here, and the slide can start after some time has passed, here 0.5 seconds. And of course this continues and the slide starts to flow. Of course this happens very slowly in a dense slide. And after a while, a quite long time, you reach again the final slope inclination as shown here. And this is a rather steep slope because we started quite densely packed. We will now see a different example when we start with a loose backing density. Here you see that the pressure, that the effective pressure is very low and that the pore pressure is very high. So all the grains are supported by the liquid. And that of course leads to a very unstable behavior. And the model predicts exactly that. And you see here a rapid collapse and a very fast and long run out. And after basically 2 seconds, the slide reached its final run out. And also the final slope is very, very shallow. So a loose slide, a loose granular material can sustain only very shallow slopes. And again, you see here as a dashed line the comparison to the experiments. And again, this fitted quite well. I have to say we are a little bit off with the time scale, but from the final run out, and we are matching the experiments quite well. And again, this should be good enough for all practical purposes. Here, one last thing I really liked about this work. You really start to see a lot of different effects, a lot of complex effects, all through the model is very, very simple. So we already saw here, you see the picture of the experiment, and we already saw that this triangular block was moving like a block. You can really observe the same in the simulations. And of course, this block will eventually disintegrate and just run out. The same in the experiment as in the simulation. The loose experiment on the other side will collapse catastrophically. And here you see all kinds of very low density flows, something like a turbidity current. And also here at the front, you can observe hydroplaning. So the grains are sliding off on a cushion of liquid. And also that is represented in some way in the simulation. So this turned out quite well, and we are again confident that we can use this framework to simulate subaquatic landslides and also landslides that move from air into water. And now everything that was to do was to put all the developments together. So we want to take the wave model and combine it with the landslide model to run a unified simulation of the whole process. And here you see approximately the concept that we used to combine these different concepts that we used for the wave and for the slide. And again, I want to remind you, for the wave, we use these markers that are always either 1 or 0, such that you have a sharp interface that can represent a wave very well. And we had these phase fractions on the granular material. And a way to combine this and see at all were the first to do this was to solve the wave model in the pore space of the granular flow model. And of course, if there are no grains, the pore space will cover the whole space, and we come back to a pure wave model. Here you see how the model is built up. So here, marked in red, is the multi-phase model for our granular flows, for our landslides. And here in lighter red comes the granular rheology, the plasticity model, and the critical state theory. And in there, we put in our wave and interface and sharp interface model. So now it looks quite a lot, but it's still quite a simple model that has just a few material parameters and that can make actually quite complex predictions. But of course, we didn't apply it yet to landslides and tsunamis. So we started validating this model with the experiments of Viroulet from 2013. And it's again quite a simple experiment. Here, this red part, this is a pile of granular material. Here you have a door that is opened, and here in blue you see a water basin. And the granular material will of course fall into the water basin and generate a tsunami there. You see here now on the left side pictures from the experiment. Here the granular material down below the water, and on the right hand side you see the simulation of this experiment. And now we have kind of three phases. We have the granular phase, I show it in red here. We have the air phase, kind of as a passive phase in white, and we have the water shown in blue. And because we have three phases, we kind of need this triangular shaped color bar, which indicates which mixture of material we have. But again, the water surface has to be sharp to represent a tsunami accurately. So our model takes care of this, and we can also show a solid black line for this interface. And as soon as we start the experiment or the simulation, you see the material falling into the water. The same happens in the simulation, and you can see here a waterfront starting to penetrate the initially dry slide. And of course, more and more of the slide is submerged and more of the water is pushed out of the slide. And soon you have a completely submerged slide. And here are a couple of bubbles leaving the slide at the tail. And of course, a wave forms here that travels away from the shore here. And after a while, again, we reach our stable inclination. And again, because of the plasticity model, also the slide reaches the stable inclination and then stays stable. And as common in tsunami experiments, also here we had wave gauges at different positions recording the wave. And as before, we can compare the simulation to the experiment, and we see a really, really nice fit of the maximum wave amplitude. And again, this is the most important result of these simulations from a practical point of view. And one thing that's very important to note here is that we did not have to optimize the material parameters to produce this wave. As I said before, the material parameters are very few and they are rather simple, just friction coefficients, grain diameters, and densities of the water and so on. So these can all be determined before an event happens. So we can actually do real predictions without having to do any optimizations on final results. And we wanted to show that we can do that. So we also ran a case, a real case. Of course, it already happened. This is the Lake Askja landslide tsunami. It happened in 2014. And you can see here the slide that fell into the lake, and it generated a tsunami with 15 meters of wave amplitude, and the inundation height, so how high the water was traveling up on the opposite shore, was up to 70 meters. And we have here a very accurate documentation, because you see it snowed the day before, and the water washed away, the tsunami washed away the snow, and therefore we could very accurately determine how far the tsunami was running up on the slopes. And we ran a simulation of this. We used a numerical resolution of 30 million cells, so it was quite an expensive simulation. It took 120 gigabytes of memory, and we ran it on a cluster, and we used 220 Xeon cores to do this. And of course, we used only material parameters as we would have used it without knowing the event would happen. So we did not optimize the wave to the measured inundation. This would also not have been possible because we could only run 2 simulations because they were so expensive. So not a lot of possibilities to optimize actually. Here you see the simulation. You see here where the slide started. The slide is colored following the velocity, and the lake down here is colored following the elevation of the water level. So right now the lake is at rest, so it's at 0. And when we start the simulation, it takes some time, but about after 25 seconds, the slide reached the shore, and of course it impacts in quite a violent manner and generates this 50-meter tall tsunami that is running across the whole lake and running up around on the opposite shores and around all the lake. And after some time, the water level calms down again, and we again reach a constant level, which is of course a little bit elevated because we now have an additional slide in the lake. As I said before, the outlines of the tsunami, they could be recovered very accurately because of the snow that was washed away by the tsunami. And here you see the inundation height that was measured after the event in the field. And you see here it's running up to 70 meters in this area. And of course, with a little bit of processing, we can get the same data out of our simulation, and we plotted it here next to each other, and it fits quite well in most regions. There are some outliers, like here it is a little bit too low, here it is a little bit too high, and we think this happened because the slide was not homogeneous when it started. We think it was a little bit looser on the right side here, and it was a little bit denser on the left side here, so that in nature it was going more into the left side than in the simulation. But overall, the fit is quite satisfying, especially considering that no optimization was involved in this simulation. For comparison, I also plotted the results from previous investigations using simpler Boussinesq and shallow water models. And they are about as good as our Navier-Stokes type model, but these models have been fitted to match the inundation. So without fitting, we are approximately as good as the old models with fitting. And that, of course, from a practical point, brings us quite a step forward, because we can actually now think about doing real predictions rather than recalculations after the events happened. And yeah, that brings me to my final conclusion. So one thing that was very important was this sharp water-air interface and the Navier-Stokes equations in order to consider complex wave patterns. We have, of course, breaking waves, we have plunging waves, all kinds of complex turbulent behavior. And if this is not simulated, your result will, of course, be off. Of course, very important is the granular rheology. Otherwise, you will have no idea how fast your slide moves, and as a consequence, you will have no idea how high your tsunami amplitude will be. Then effective pressure and excess pore pressure, of course, coming back to Vaillant, we saw the devastating effect that pore pressure can have. We also saw it in the simulations, how unstable granular material can become if there is high excess pore pressure involved. And of course, with that porosity, the latency, and also the exchange of pore fluid in the slide is very important. And we account for all those few things in our model, and therefore get some quite reasonable results for the cases that we were running. Yeah, that was it from my side. Here are my social links and my mail. If you want to read the paper, they are all linked there. If you have more questions, you can drop me a message there. You can also drop me a mail. And I'm also, of course, very happy to answer your questions now.
Excellent. So yeah, thanks a lot, Matthias, for a really brilliant, very visually stunning talk. So yeah, I'll open to questions. You can either raise your hands or just unmute yourselves, and we can deliver them to Matthias now.
Hey, nice talk. Can you hear me?
Yes.
Yes.
Okay.
Thank you very much.
So one of my questions would be that you said that there's no fitting involved, and then you can run it, and then it can give predictions.
Mm-hmm.
So if I have like a mountain next to a lake,
Mm-hmm.
how do you know where does the mountain slide down, or like how can it predict that?
Yes, that's a very good question. And basically, I get around that by saying we start with failure. So this is, of course, a flow model. So we start when the mountain failed. There are, of course, other models that can predict the stability of a slope, but they are usually focusing on small strain. So the flow model is always involving large strain, big displacements, and they can handle this. They can handle these cases very well, but they kind of fail in this small strain and stability analysis type of problem. But for this, we have other applications, basically solid mechanics applications. So how I would solve it was to run a solid mechanics application with some very advanced soil mechanics models, and that should give me the failure plane. And once I have the failure plane, I can continue in my framework with the propagation of the slide and the generation of the tsunami. One reason why the Navier-Stokes the Navier-Stokes equations break down for stability analysis is that you divide here by the shear rate. And the shear rate in a stability problem is 0. So you kind of divide by 0 and you get out not really physical results.
Yeah, I mean that makes sense. It's a different problem. So at the start, it's just like, oh, you have the mountain, and then it sits there for I don't know how many thousands of years, and then suddenly you have some water coming in, and then it can't deal with it, and then you find the plane, and then you can use this one.
Exactly.
But now I'm thinking like what would be the difference between like having just like a solid block moving into a water compared with the porous one, like rock versus beads? I'm not sure how different would be. That probably would be.
I mean, there are a lot of experiments of blocks. Basically, the Birolais let a granular slide one into the water. There are a lot of experiments of people that just push the block in.
Yeah.
So of course it also generates a tsunami. But of course the block
probably different
is not
slide, like slightly different style or something.
Yeah, it's behaving a little bit different because the slide is deformable. So because of that, you have a difference. The velocity in the slide is not uniformly. So you can also, decelerate the front of the slide while the back is still moving with the same velocity. And then, of course, you also have water penetrating the slide, as you can see here. So this is kind of damping the wave.
Yeah.
It's damping the deceleration of the slide, and it's also damping the wave. So a block that moves with the same velocity as the frontier would generate a higher wave.
Yeah, probably something.
Yeah.
Yeah. I mean, I'm sure somebody wrote an article about comparing some stuff like that, but
yeah, there is a lot of literature on that, yes, and a lot of experiments with blocks. And one last thing, as you said, the initial stability is a different problem, and you usually also don't use the Navier-Stokes equations in that case. So you don't use the velocity here as a unknown field. You use the displacement, and you don't use the shear rate, but the stretching tensor as a measurement for the stress. So as you said, more or less a different model.
Yeah.
Excellent. So any more questions out there? I think Philippe has got a question.
Yeah, hello, Matthias. Thanks for the talk. I think it kind of similar question to the previous one. On your slide 28, do you have several grain size to measure the different height of the wave? I guess like big grain would make a bigger wave, and small grain like sand would make a smaller waves. Does that have an effect? And maybe on the like tsunami, different grain size would affect the waves at a different space?
Birolais actually ran this exact experiment with 3 different grain sizes. We simulated all 3 of those experiments. They are in the supplementary material of my last paper. I don't quite remember where the wave was higher, but basically what happens so the biggest effect is that the drag term is much higher when the grains are small. So the water penetrates the slide slower in a fine grained slide. And therefore this front of water goes into the slide slower. if I can remember correctly, it had a very low influence on the wave amplitude, but it had an influence on how the slide was decelerated by the water.
Okay, so I assume in your tsunami simulation, you've used the uniform grain size.
Yes, so that's another thing. In the experiments, Virolai used uniform grains, which was very convenient. For the real case, so for the Askia case, I think as you can see here, and you can of course imagine, you have all grain sizes. The model can only simulate uniform grain sizes, so we had to choose one. And we then used we used some literature to find out which grain size might be appropriate to use for the distribution that we have here. So for example, the friction coefficient mu is a function of the grain size. And there is a paper stating that the average grain size can be used to calculate an average friction coefficient, and that gives you quite good results. So we used that there, and for the permeability, we found similar indications in literature on what to use. So also there we came to a conclusion on which grain diameter to use. And one more thing, as I said before, the wave is not highly affected by the grain diameter, because a slide with smaller grains displaces more water, but is also deaccelerated more quickly. So this uncertainty was not fully propagated to the final result, which was kind of lucky in our case.
Okay, excellent. Thank you.
Welcome.
Well, if we don't have any other hands up, I've got some probably a lot of overlap with the previous questions that I had ready. But I guess one of the main things that stood out to me is that in your Flume experiments, you were getting really good spatial fitting, but as you say, there's a bit of temporal difference, right? The time dynamics were a bit out with the comparison to the experiments. And then when you did this really large scale, very complex tsunami scenario, the actual length scales you were getting, this inundation height, that was also spatially looking quite good. So it does look like to maybe take the next steps along could be to understand why the temporal dynamics are a little bit out. Do you have any kind of insights or hypotheses as to where that discrepancy originates?
Yes, I mean the biggest temporal error is in this experiment, in this simulation here. So of the submerged granular collapse and the dense case that collapses very slow. And you see here after 3 seconds, the pile in the simulation, the collapse advanced quite far already, while it didn't advance so far in the experiments that's shown here as the dashed line. And the reason, I think, is, well, there are different kind of angles you can look at it. So one view to look at it is that this line here, this critical state line, this is actually not a line, but rather a band, which in you find kind of stable states. That means you can have a dense state, and your pressure will then not be so high as the line predicts, but you can be a little bit off, so around here. And only after shearing you will move into the critical state and towards this line. So you start here and then move slowly towards this line, while I in my model assume that I'm always on this line. And that of course leads to the fact that I overestimate my particle pressure, and thus I overestimate how quickly my grains will be pushed apart so that they can collapse. Or a different point of view to look at it is that I'm missing a bulk viscosity. If you look at the model equations here, you see that we have a shear viscosity, but we have no bulk viscosity. And of course, the material is also, it doesn't want to dilate or to contract. So there is a resistance connected to this one. And this resistance would be called bulk viscosity in the Navier-Stokes equations. It could be, it's representing the exact same thing than in the critical state theory, but I think this is missing here. And I think this would be the next step to really improve the results.
Nice. Yeah, no, that sounds really good. So it's the structure of the equations rather than any kind of parameter fitting or model complexity. You know, you're thinking because the final shape and the intermediate shapes are quite similar, the timescales really set by these hidden evolution, or for your model at the moment, they're hidden or they're, you know, not resolved. Okay, yeah, that's
and yeah, I mean, there is not much left to fit. Like there are parameters like the particle diameter and the densities and the viscosities, and they are all given. Also the friction coefficients mu are given. So there is not much space for optimization of parameters to improve anything here.
Nice. Excellent. So assuming we have no more questions from the audience. So yeah, I'd like to thank Matti again for a really excellent talk, and it'd be great to hear about your new life as a software developer, but of course I'll probably be emailing you about this rather than your new stuff. So.
Yeah. Thank you very much for the invitation.
Cheers.
And yeah, if you have more questions, you know how to reach me.
Yeah, brilliant. Okay. Hope you have a good rest of the day. We'll talk soon.
Thanks to all of you too. Okay, bye-bye.